is a joint work with Yuka Hashimoto, who gave a talk in the morning session, and other guys are Masahiro Ikeda at Riken and Yoshinobu Kawahara at Osaka University. Okay, so yeah, and this is the outline of my talk. And in the first section, I will explain my motivation and some methodology for the data-driven analysis for dynamical systems we using a Koopman operator and function spaces. And then in second section,
cannot see your slides and be moved.
Okay.
Yeah, people here cannot see the slides.
Okay, I see. I see. Sorry. There we go. Okay, and in the second section, I will explain our proposed method, JetEDMD, we call JetEDMD. And this is a kind of finite dimensional approximation push forward using RKHS. So yeah, in my talk, RKHS is the main function space to consider. And so yeah, so I will explain some details of RKHS as well. And in the third section, as applications, I explain some data-driven reconstruction of analytic vector fields. Then in the last section, I will explain, I will introduce the notion of rigged Hilbert space, and I will explain some numerical results for the approximation of eigenvectors for the extended Koopman operators. I will explain the extended Koopman operators later here. Okay, so let's get into the first section. So actually, maybe almost everyone knows the definition of dynamical system here, but to fix the notation, I will explain the definition. So let X be a set, then the dynamical system is a map from X to X. And dynamical system is, the definition is quite simple, but it's one of the fundamental and maybe one of the most popular mathematical model to express, to represent some data in the real world. And so for example, if we have such a finite data, here finite pairs of data, then maybe we may assume, or in many cases, we may assume that there exists some dynamical system that represents this data. Okay. So actually, the keyword of my research is the data-driven analysis of dynamical system. So the aim of the data-driven analysis for dynamical system is to extract some essential information of a non-dynamical system from data like this. So if we have such a discrete and finite data, then we want to find some characteristic, or we want to extract some essential information of the dynamical system. Yeah. Okay, so I think there are several approaches for the data-driven analysis of dynamical system, but we employ the Koopman operators. So first we fix the function space on X. Yeah, X is the state space where the dynamical system acts, and then we consider the Koopman operator or its dual of dynamical system on H. And then we try to extract some information of F using functional analysis or real analysis or complex analysis or other method. Yeah, and this is the definition. Yeah, and yeah, but the Koopman operator is also called pullback or composition operators. And yeah, and in math, or for example, in complex analysis of a function space, function theory, composition operator is a kind of popular name. And pullback is sometimes used in the fields of geometries. So yeah, The coupon operator is sometimes usually used in physics or data analysis. And the definition is as follows. So for let X be a set and let F be a dynamical system, and then let H be a function space, then the coupon operator is defined as a linear operator defined by the composing the function with F. Yes. Yeah, and in my talk we use this notation to describe the coupon operator, CF. Okay. So let's get into the second section. So first I fix the notation. So in this, so let X be the open set, open domain in the complex and affine space of dimension D, and let F be a holomorphic dynamical system. Actually, this assumption that holomorphic is essential when we prove some theoretical results. So we assume that. But when only consider some algorithm, we don't need this assumption. Yeah, and we fix a closed ball center P in X, and we fix a compact convex set that includes the image of K under F. And we denote the space of analytic functions on the compact set S by AS here. Yeah, the analytic function on S means that a function that can be analytically continued to some neighborhood of S. Yeah, and we equipped AS. We equipped some topology. We equipped some good topology with AS. Yeah, but I don't explain because the topology of AS are a little complicated, so I don't explain the topology. Yeah, then if we have such a notation, if we have such a setting, in the setting we can define the pullback, and it is almost the equivalent notion of two coupon operators. And so we can define the pullback F star. It's a continuous linear from L to AK. And then we can define the push forward, or it is almost the same as the Perron Frobenius operator, and it's a dual operator of the push forward, pullback. Yeah, I forgot to write, but it's a dual operator, and it also means dual operator. And yeah, and it's actually the coupon operator. So coupon is everywhere. So yeah, and actually push forward satisfies this formula. So yeah, actually, so the push forward contains the entire information of the dynamical system. Yeah, so we can say that if we understand the push forward, then we understand the dynamical system, I guess. But actually, by definition, F star is quite abstract and kind of transcendental. So it's almost impossible for us to estimate F star itself from finite discrete data. So we change the problem. So we change and we construct some good finite dimensional subspace and consider the estimation of the push forward and push this direction push forward to that finite dimensional subspace. So we define the derivative of Dirac delta. So for point X and D non-negative integers, so we define delta alpha xh by the evaluation of the derivative of the function at x. And we define the finite dimensional subspace dPn by the linear subspace generated by the derivative of Dirac deltas of order up to n. And we denote the union of dPn over n by dP. And we remark the DPN actually coincides with the dual space of NZ at P. And here, NZ is a kind of higher order generalization of the tangent space, and it's very classical notion known in differential geometry. Yeah, it's not airplane. Yeah. So the space of jet satisfies quite nice properties. Satisfies nice properties. For example, so the dimension dPn is described as this n plus dt. It's a binomial coefficient, and dp is dense in AK, the dual space of AK. And the last one is the most important. So the F star preserve the space of jet dPn here. So because dp is dense and F star satisfy this condition, so maybe we can. I think we can say that the distraction of push forward to the dPn is a kind of good approximation of push forward. So the next problem is how to estimate it in data-driven manner. Okay, so there are two estimates the distribution, the push forward, the RKHS reproducing kernel Hilbert space plays an important, the essential role. So we fix a Hilbert space included in the space of analytic functions, and we denote the inclusion map by iota, and we assume that the iota is continuous. And actually, the continuity of iota is almost equivalent to that H is RKHS. And there are many examples of RKHS, but we will introduce the Fock space later. And definition of RKHS is as follows: some Hilbert space of functions of x, and it's so if we say that H is RKHS if any evaluation is continuous for So this is the definition of RKHS. Okay. So let me explain some details of RKHS. And so by the least representation theorem, there uniquely exists some function in H such that any evaluation is represented by the inner product with Kx here. Then we can define the two-variable function on X, and actually it becomes positive definite kernels. And here, positive definite kernel is a two-variable function that satisfies that for any finite element in X, this matrix becomes a Hermitian positive semi-definite. So, and by the famous theorem by Murat and Aronshine, and so if we have, conversely, if we have a positive limit kernel, then we can show that there exists an RKHS such that the element Kx induce that positivity kernel K here. And moreover, we have more stronger result that if we have a Hilbert space continuously included in AX, then we have positivity analytic positivity kernel. So there exists a one-to-one correspondence between the continuous Hilbert space continuously included in the AX and the analytic positivity kernel. So maybe there is an expert of RKHS here, but so RKHS is usually introduced with the positivity kernel, but I think that regarding RKHS as a good Hilbert space continuously included in such a large, nice space provide us some theoretical insights. So this interpretation is, I think it's quite important. Okay, so let me explain the jet EDMD. So this is a kind of data-driven approximation method for push forward. So we regard that we identified the RKHS with its dual via the Lee's representation theorem, and we assume that the point P is a fixed point over F. Actually, we can modify we can this condition, but for simplicity, we assume that P is a fixed point, and then we define the Vn. This is the linear subspace of H, and it's defined as the image of dPn under the dual operator of the inclusion of iota. And we denote the dimension of Vn by Rn. And then we fix an orthonormal basis of Vn, union of Vn, and we assume that the first Rn elements of the basis constitute the basis of Vn, like this. Yeah? And we call this orthonormal basis intrinsic observable or intrinsic dictionaries. Then we define a kind of feature map. We define the Vn vector Vn, and we define the Vnx by piling these vectors. Okay. Okay. So yeah, let me explain some the examples of the Fock space. So the Fock space is it also appears in the Igor's talks, and Fock space is RKHS and composed of homomorphic functions on CD such that the L2 norm of function is with the Gaussian weight is finite. Then if we define this function, then so these functions constitute the intrinsic observables in Fock space. Yeah, this function is a kind of this function is the product of polynomial and exponential functions. Yeah, by this proposition, these functions constitute the orthonormal basis of Vn. And we also remark that if we take a P at 0, then this function becomes a polynomial. So monomial. So so when we consider the EDMD, monomial is one of the popular choice of dictionary, and but in our framework, monomials quite naturally appears. Then actually, our jet EDMD is a kind of refinement of EDMD. Also, if we have a data generated by dynamical system, then we fix an integer m and we fix some large integer n. Then first we construct the matrix using the intrinsic observable. Then we truncate this matrix to the leading submatrix of order Rm. Yeah. Okay, so this is the illustration of the approximation of push forward using RKHS. And yeah, first, we actually want to approximate or estimate this push forward, but it's almost impossible. So we fix RKHS, then we construct the good finite dimensional subspace. Then actually this is a good approximation of push forward. Then we can show that this arrow can be approximated by this matrix, and this is constructed only from data. And when we consider the Fock space, this arrow actually coincides with the Fourier transform here, and we can employ some more deeper analysis using the theory of Fourier transform. And actually we can show the convergence of, we can show this approximation in rigorous manner. Yeah, this is the theorem, convergence theorem. So, I won't explain the details, but the point is that, and so if we consider some truncated truncation of matrix, we can show that if we have sufficiently many data, then the matrix constructed from data and matrix of the matrix of the restriction of the push forward get close when we take large M and N. Yeah, and I will end this section with some remarks. So actually the truncation is essential to prove the convergence theorem. So yeah, actually, so in Fock space, no nonlinear map induces a bounded Koopman operator, and it's a kind of obstruction to prove the convergence of the DMD. But if we truncate the matrix, we can show that the convergence. So if Koopman operator is bounded on RKHS, we don't need to truncate the matrix. So we consider some Segre kernel, then we don't have to truncate the matrix. And as I said, that the monomials is naturally appears. So in my context, in my framework, and the monomials is one of the popular choice of the observables. So, and actually monomials have some good performance when we consider the EDMD and jet EDMD explain why monomials have good performance. And also actually this is the matrix for EDMD, but it's a kind of linear approximation of the nonlinear dynamical system. But jet EDMD provides some more clear relation between the push forward and the matrix constructed from data-driven, constructed from data. So yeah. Yeah. So okay, let me explain. But I have maybe 5 minutes or something. So let me explain some.
Just want to leave a couple minutes for questions.
Okay.
Yeah.
Okay. Let's get into the third section. Okay, so what I briefly I explained the data-driven reconstruction using this diagram. So actually, so we consider the Fock space, and we consider the ODE like this, and we denote the flow map by phi t. Yeah. Then actually the FA, this vector field is described using the operator. So just considering the feature map and then send this element with this a kind of generator of the Perron-Hormez operator, and then consider the gradient at x equals 0. Then we have some operator theoretic representation of FA, but actually we don't know. We can't approximate, so we don't know this operator, so we replace it with the approximation. So then we consider this direction. Then this is actually the approximation of FA, and we can show that this function and this function actually get close when we take large number of data and large M and N. Yeah. So and then we consider the numerical simulation for Lorentz equation. So then we consider the flow map phi 0.1. Here we take the delta t of 0.1. Then we consider the samples, 300 samples in the cube domain. Then considering the approximation of the analytic vector fields, actually it reconstructs the Lorentz equation only from this data and the image of them under F here. Yeah, and I will end my talk with some remarks about for the approximated eigenvectors of extended Koopman operators. So, yeah. So, first I will explain some definition of the rigged Hilbert space. And so let H be a Hilbert space and let V be a dense topological subspace with finite topology. Then we call the triple VH and the dual of V prime, dual of V a Gelfand triple. And we call the Hilbert space rigged Hilbert space if H has such a triple structures. Then if we have a linear operator that preserves the dense topological subspace, then we can define the extension of linear operator like this. This is just the restriction of the adjoint vista, and then we take a dual, then we can define the linear operator on the dual space of V. Then actually we can show that this operator is extension of the original operator. Then actually our situation matches the framework of rigged Hilbert space, and so actually the union of Vn is dense in H, and the Perron-Lorentz operator preserves the V. So and actually we can show that the projective limit of Vn coincides with the dual of V, and the extended Koopman operator here is actually the limit of the adjoint of Koopman operator, the restriction by adjoint of Koopman operator. The limit of adjoint of the restriction of the Koopman operators like this. And we can approximate this using jet EDMD or EDMD. Okay, and this is the numerical computation, and we can compute the eigenfunctions using we can approximate the eigenvectors of the extended Koopman operator. Well, actually, extended Koopman operator is defined on a kind of linear functionals of the observable. So the eigenvector is not eigenfunctions of Koopman operator. So it is non-trivial that the eigenvector has some eigenvectors has good properties for the structure of a dynamical system. But actually, we have some numerical result for this.
I'm going to have to ask you to wrap up. I'm sorry, just in order we can keep with our schedule.
Okay. So yeah, I will. Okay. So yeah. So this is the NO map, numerical result for NO map, and yeah, and actually it captures some structure of dynamical system. So yeah, but it's only the numerical observation, so we have to develop the theoretical aspect of the eigenvectors of extended Koopman operator. So, okay, this is the conclusion of my talk, and thank you for listening.